3.1, solve linear systems by graphing. So just because these tend to end up giving us some confusion, I know these are in your notes, but I'm just going to rewrite them just to talk about them really quick. But if we say that it is consistent, that means at least one solution. If it's inconsistent, there's no solution. And then, so we would always say consistent or inconsistent, and then we will say independent, which means exactly one solution, or dependent for infinitely many solutions. So if it's inconsistent, it's just inconsistent. But if it's consistent, then we have to also say it's either independent or dependent. And so we had if it intersects at one point, there was those little graphs at the bottom, but that's consistent and independent. If it is basically two lines on top of each other, that would be the consistent and dependent. And then if they are parallel lines, so no intersection, it's inconsistent. So just wanted to do a quick review there because that tends to be an area of confusion. So when you do this section, I would say I recommend graph paper probably when you're doing your homework problems because of counting and lining things up. These ones tend to be a little nicer, so if your spacing is at least correct, you should be fine. But the ones in, I want to say it's the pre-cal book, are not very nice, and they give you things like 9.3 is the intersection point, and it's like you would never get that if you don't have graph paper. So you're like sitting there, just guessing. So these first ones say to graph the linear system and estimate the solution, then check the solution algebraically. So I'm going to see if I can put up my little graph here. Okay. So number 4, we have y equals 5x plus 2 and y equals 3x. So these ones are already in slope-intercept form, so they're pretty easy to graph. So I'm going to just go ahead and set up my graph. I usually end up overestimating a little bit of what I actually need when it comes to these because you never know where the intersection is actually going to occur. So I would recommend, I like to do my lines in 2 different colors, but it's up to you. I mean, if you just want to do them in pencil, that's also fine. So for my first line, that's going to be a y-intercept of 2. And then I have a slope of 5, so I'm going up 5 and right 1. 1, 2, 3, 4, 5. Or down 5 and back 1. And then I can connect my dots, more or less. So then my other line has a y-intercept of 0. And then we are slope of 3, so up 3 over 1. And as soon as I pretty much see that there's no way that's going to intersect up there, I'm going to want to go down and back so that I can try to find the intersection point down and see if it's there. So 1, 2, 3, and back 1. So that's on a point that we actually graphed from the last one. So my intersection point is right here. So what is that point?
-1, -3.
-1, -3. And you can plug the point back in to check it as well and make sure that the point is actually a solution to the equation if you wanted to. I'll just show you really quick. So if we plugged in -3 equals 5 times -1 plus 2, -3 equals -5 plus 2, so -3 equals -3, and so that works. That tells us that that is a solution, or that is the solution to the equation. And as long as it works in one of them, it's fine. You don't have to check both of them. Because if it doesn't work for both of them, something's wrong, so. And sometimes, not necessarily as much with the graphing problems, but when we start doing these same problems algebraically instead of graphically, I do have a tendency to offer a bonus point for actually checking to make sure that it worked. Because in that way, there's never confusion on if you have the problem right or not. So I try to incentivize checking your work. All right. Number 10. We have y equals -3x minus 13. And we have -x minus 2y equals -4. So I would, first of all, get the second equation into y equals mx plus b. But I will say, a lot of times if we were graphing the first one, just graphing a line, we'd probably count by 2's on our interval. I would say don't do that. I know it's going to make a really big graph, but it could be confusing as to exactly where it is. I mean, if you want to do that, it should still be fine, but I would probably not. I don't think there's any other ones that are really that big. So anyways. So go ahead and get the second line solved out. So -2y equals x minus 4. So y equals -1/2 x plus 2. And usually once I have rewritten the line, I will actually cross out the one that it originally was replacing, just to make it not confusing. I can actually graph this one over here so I have plenty of room. All right, so first one, y-intercept of -13. Oh, it moved, so I lost count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And then I would say, based on what I see about the other graph with it having a y-intercept of 2, I would be counting my slope up and back instead of down, because there's pretty much no way that it's going to connect down at the right. It's probably going to connect more up at the left, just based on what's there. Could be wrong, but just a guess. So -3 slope, so up 3, back 1. And I know a lot of times we say, like, just graph 3 points and then connect the dots. I don't do that with these ones because I want to make sure that my stuff is lined up exactly. And then second line, y-intercept of 2. And this one, just because of where the line is, for the first one, I am going to go down and back, again, because there's no reason to go up and to the right. It's clearly not going to cross over there. So, rise, so down 1, back 2, down 1, back 2, yes.
It's a negative slope.
LOL, thank you. Oh, whoa, come back, come back. So I lied. Up 1, back 2. So what is that point of intersection?
-6, 5.
Yep. So then again, you could plug this in to check it if you wanted. Oh, I have your ID card.
Oh, goody.
Also, if you want to give Hope hers.
Yeah, I can.
Ariel, you're not going to the game today, right?
No. Or tomorrow. Thank you. Oh, fantastic.
All right. Let's see, number 12. Y equals 4x plus 3 and 20x minus 5y equals negative 15. Oh, negative 6, 5. And you could plug it in to check it. I'm not going to check this one. So we need to get it in y equals mx plus b. So negative 5y equals negative 20x minus 15. If I divide by negative 5, y equals 4x plus 3. Now what do you notice?
Same equation.
What does that mean?
Parallel.
Same
No.
line.
They're the exact same line.
Oh my gosh.
Parallel would have the same slope, different y-intercept.
Same thing.
So these are the same line. You do not need to graph it. All you need to say is infinitely many solutions.
So confident too. It's like, that is parallel.
So if they come out to be the same line, you do not need to graph them. You can just say infinitely many solutions. All right, so for the next ones, it just says to solve the system, then classify the system as consistent and independent, consistent and dependent, or inconsistent. So you don't really need to graph those. You need to have the equations of the lines, like y equals mx plus b. But if we have the same slope, different y-intercepts, they're parallel, so there's no solution, so it's inconsistent. And I want you to tell me no solution, inconsistent. If you don't write no solution, like your answer is not completely correct, because that would tell me you're kind of just guessing on what it is. So make sure you write no solution if it's that. If they have the same slope, same y-intercept, it's the same line, so it is consistent and dependent. And then if there is just one solution, so they're just lines that are going to cross, which everything crosses if it doesn't have the same slope. So anyways, so anything that's just two lines that would not be parallel or not the same line. It's going to be consistent and independent. So you would not need to actually graph them. I mean, you're welcome to if you're just so ambitious, but you don't actually have to. When we actually get to the next section, we would be solving them algebraically and not graphically, so it's like might as well just get used to that kind of now. Or maybe not the next section, but I don't know. In the next couple of sections, that's what's going to be happening. So, number 18, we have the line 2x minus y equals 4, and x minus 2y equals negative 1. So we need to get them by themselves. So I'm going to actually pull this top one over here and solve it out on this side, and then I'll just do the other one underneath of it. So I would have negative y equals negative 2x plus 4, and then divide by negative 1. So y equals 2x minus 4. Then the other one, subtract x, so negative 2y equals negative x minus 1. Divide by negative 2, y equals 1/2 x plus 1/2. So how many solutions am I going to have for this one? Or like, how would you state what it is?
Consistent and independent.
Yep. Consistent and independent. So, and also the way, because I know that this can be confusing, the way that I remember if it's independent is if there's only one solution, because if you're independent, you like to do things by yourself. So, that would just be one. Let's see.
I'm confused on how you like figured it out without graphing it.
So I just looked at the slopes are different. So because they have different slopes, they're going to have to intersect somewhere.
Oh.
So the thing is if I graph them, they may not intersect until way out somewhere. Like you just don't know. And so by just looking at it, you can tell if it's going to be one solution. If it had the same slope, different y-intercept, I would know they're parallel. Parallel lines never touch. And then if they're obviously the exact same equation, you know that they're just going to be on top of each other.
Yeah.
So
And then the independent was from.
how many solutions you had. So because these are of two different slopes, they're going to only intersect in one spot. Do you have a question?
No, I was just confused with myself. I'm okay now.
Let's see. We've got y equals 2x minus 1 and y equals, or sorry, not y equals, that's what we hope for, negative 6x plus 3y equals negative 3. So top one's already in the right form, so I'm just going to manipulate the bottom one. So add the 6x, so 3y equals 6x minus 3. Then divide by 3, y equals 2x minus 1. So, what are those lines?
Consistent and dependent.
So they're the same line, so they are going to be consistent, and then because they're the same line, there's infinitely many solutions, and so they are going to be dependent. And we would want to know infinitely many solutions as well. So go ahead and get in the habit now, because when you get to solving them algebraically, you're going to actually have to write that there are infinitely many solutions. So get used to writing that there. And the book does say to solve, but you're going to do graphing ones from the first section, so like that we did up here, you're going to do those graphing, so the other ones you can just look at them and tell me. If you are just so ambitious to want to solve them, you can. It's fine by me, but let's see. 28 5 halves x minus y equals -4, and 5x minus 2y equals 1/4. So start with the top one. I'm going to have -y equals -5 halves x minus 4. Then divide by the negative, so y equals 5 halves x plus 4. And then the other one, -2y equals -5x plus 1/4. Then divide by the -2, y equals 5 halves x minus 1/8. Okay, because 1/4, if you divide that by 2, it's the same as multiplying by 1/2. So we notice about these lines. They have the same slope, meaning they're what kind of lines?
Parallel.
They're parallel lines. Okay, so that means that there is no solution. Okay, because there's nowhere that they intersect, and so this would be inconsistent. So any questions about these ones? Are we okay with these? All right, so your problems 3, 5, 11, let's see, 17, 19, and 21.